welcome back to AGT STEM. Today we're going to be watching a video about holmium. It's a pretty long video, so hopefully stick with us to the end. Let's get to it.
Sometimes I think of it as a very pedestrian element. It's something that doesn't have very many applications, so it's quite easy to overlook. But at the same time, some of those applications are actually really important, so you have to remember that, like a lot of elements in the periodic table, it can be very easily overlooked, but actually it's got some really fantastic uses.
When I think of...
A lot of people overlook holmium. That's what we know so far. And make sure you notice holmium. He feels very left out sometimes. You got to pay attention to him.
The element holmium, I think of the English word hobble, which may sound a bit funny, but it's because there's a simple way of remembering the names of all the lanthanide rare earth elements. Let me show you. It begins with lanthanum and goes languid, centaurs, praise, Ned's promise of, you put that in, small European garden tubs. Dinosaurs hobble erratically, thrumming yellow lutes. So there it is, number 67, holmium, which you remember through the word hobble, which begins with the same letters, H-O. I learned this, I think, when I was at school. It's really great. I can write the whole row of lanthanide elements on the blackboard or whiteboard nowadays, and the students say, wow, and think I'm a genius.
Holmium was first observed, not sort of isolated, but observed spectroscopically by two chemists in 1878. One of them was called Marc Delafontaine, and the other was called Jacques-Louis Soret. They saw this wonderful spectrum and they thought, this must be something new and different. They were obviously great PR guys because they called it element X.
I don't know much about holmium, except that it's named after Stockholm, or the Latin name for Stockholm. I know also that there was a lot of argument when the element was first discovered. Who discovered it? Had they discovered it? Had they not?
They had actually seen it in its clean, isolated state, but it wasn't until a year later that it was actually isolated properly for the first time. And of course, one of the issues, like with many of the lanthanides, is actually isolating holmium on its own, because many of the lanthanides are of a very similar size. So you dig them out of the ground in minerals all jumbled up together, and you have to separate them out so you can put all the thulium in one pile over there and all the holmium in one pile over there. And this is quite difficult to do, but eventually people have figured out how to do it.
The other thing I know about holmium is that at low temperature it exhibits very strong magnetism. It's not much use at room temperature, but because of the number of electrons, unpaired electrons, at low temperature, you can get very strong magnetic effects.
So a year later, in 1879, a guy called Per Theodor Cleve manages to separate holmium on its own for the first time. And he decided to call it after the Latin for Holmia, which is actually Stockholm, which is his native city.
The electrons have a whole series of different energy levels, depending whether they're paired or unpaired. And the energy separation between these levels is not very great. So as you warm it up, the electrons have more energy, so some of them go into a higher state. But if you cool it right down, they all go into the lower state, which in this case happens to be the really magnetic one.
So holmium has some very interesting fluorescence phenomena. So you might be able to find some kind of application where you need something that fluoresces with a particular type of colour. One sort of spin-off from that is that and we're back to this nature of the absorption spectrum that our two folk found many, many years ago. That spectrum is very distinct and it almost never changes.
The strange arrangement of electrons means that if you put some in glass, you can get quite an elaborate spectrum. And we used to use holmium filters to calibrate our spectrometers.
Where basically you would do a run with the Holmium sample and check that the spectrometer is calibrated properly so that when you record a real spectrum, you know that the peaks are actually in the right place.
We've searched everywhere in the lab, but we don't calibrate spectrometers anymore, so we can't find the filter.
I thought all elements had a really distinctive spectrum. Are you saying that elements spectrums are not reliable?
They can do. I mean, the first thing is it depends what type of spectroscopy you're actually running, because there are many, many different types. Then the second part is an element on its own will have a very distinctive spectrum, but also most elements don't turn up in the world or are not found in the world just as the element on their own. I mean, obviously gold often is, which is why it's used often in jewellery, but most metals in the periodic table are dug out of the ground in the form of oxides, or you want to turn them into an interesting molecule to do something with them. And usually when you're changing that environment around the metal, you're changing its core electronic structure, which then means its spectroscopy will be different. But the lanthanides generally, although there are exceptions to the rule, they're not really interested in what's going on around them. And in fact, one thing I often teach our undergraduates is that whilst transition metals change a lot depending on what's immediately bonded to the metal, lanthanides by and large are sort of screened away from what's going on around them, and so you can make a really impressive fancy molecule with holmium in the middle of it, and you could record its ultraviolet visible electronic spectrum, and it would look barely any different to the free ion in the gas phase, because as far as it's concerned, it's no different. It's almost like the lanthanides are really antisocial, and they don't want to talk to molecules that bond to them in the way the transition metals do.
It is used in surgical lasers where you dope a small amount of holmium into so-called YAG, yttrium aluminium garnet, and then you get laser emission around about 2 microns, that's 2 millionths of a meter, and that wavelength is particularly good because it's strongly absorbed by water, which your flesh contains a lot of water, so surgeons can cut very precisely with the laser, and apparently the laser is also so-called self-cauterizing, so that when you cut through a blood vessel, it tends to seal the blood vessel off, so the patient doesn't pour blood, which is obviously useful.
Holmium is one of the elements in the periodic table that obeys the Oddo-Harkins rule. The Oddo-Harkins rule says that elements with even atomic numbers are more prevalent than those with odd. It just so happens that holmium is an element with an odd atomic number, and therefore it's less prevalent than its neighbours, which have even numbers. In general, what you would expect is that the heavier the element gets, the less of it there should be. But what you see is if you drew a line, it's not a nice smooth line. It keeps on going up and down, even though the line overall is decreasing. And so what this basically shows is that the even-numbered atomic nuclei are, on average, more abundant than their neighbours, which doesn't sort of make sense at first until you think about how are elements actually formed. Now, you start off with hydrogen in the universe, in suns, and that's converted into helium. And it's usually helium nuclei being pushed together that help you form heavier and heavier elements. But once you start with an even-numbered nuclei, then your products are always going to be even. So like carbon, which is 6, would be 3 helium nuclei. To get to nitrogen, which is 7, then you need to add in a hydrogen from somewhere. And that seems to be a little bit more difficult to do because most of the hydrogen had to be used to be turned into helium. So once you go into a universe with helium, you're more likely to get even-numbered elements. One, though, that is the big outlier is still actually hydrogen. And of course, that's a good job, because if it hadn't, then you wouldn't have water, which is essential for life, and you wouldn't have most of the molecules in the world, which do tend to be quite hydrogen rich. Yeah, so holmium obeys the rule because if you look at its nearest neighbours of dysprosium and erbium, there's more of them than there is holmium. So you can see there's a definite dip in between those two even-numbered elements.
I don't know. I think it's not so much it's forgettable, but you don't remember it, which is rather forgettable, sort of means that you think about it and then you forget about it. I would say most people never really think about it.
So I did say Holmium was a little bit pedestrian, but there's another fact that I've dug up about it as well, which is in nuclear processes, you want to be able to control all of those neutrons flying around, otherwise things would get out of control. And the element that normally gets the limelight where that's concerned is boron. It's really good at absorbing, but a little known fact is that holmium is actually quite good at absorbing neutrons as well. So you can kind of use it as a sacrificial element to keep your nuclear reactions under control.
I suppose one of the things that people have said, and there's an article in the latest issue of this journal, Nature Chemistry, and they have an article about holmium with a rather catchy title, Holmium, in which the important part of this article says that they think that holmium is the most underused element. Nobody has really found a good use for it. I'm not sure. I think there may be other elements that would be a strong contender for this title, but we should let them have their say. The other thing about holmium, which I think is important, is that it has a pretty prominent position on this tie. So whoever designed this tie clearly thought that holmium was important. So perhaps they've got a good application.
Well, that was a long video. Hopefully you stuck around for the end. Thank you so much for watching. Comment a heart emoji if you made it till the end of the video. Thank you so much for watching. We'll see you next time. Stay smart. Bye!